Hello and welcome back. In this video, we'll cover section 2.5. So this is a continuation of some application problems of solving linear equations. This time we'll look at some geometric applications, so some questions involving triangles, and then also working with formulas, which comes up a lot in all kinds of science classes that you might take, and then also in future mathematics courses. So our first section is on substituting values into a formula and finding some unknown variable. So in these, we'll be given a formula to use. The first one is on the area of a triangle. So let's say we have some triangle. And this can be a right triangle or a non-right triangle. And we can describe this side here as the base, and that's what they put as B in the formula. And then if we go from the top of the triangle and draw an imaginary line going straight down to form a right angle here, this is what they're calling the height of the triangle. And they will typically use an h. So the formula for the area of a triangle is 1/2 base times height. So 1/2 times this base times this height. And it's really coming from the area of a square. We could derive it from there. So in this particular example, they give us a few values to plug in. They say the total area is 30, and our base is 8, and they want us to find h. So let's just plug in. We can replace 30 for A, 8 for B, and then we'll be left with one unknown variable. So instead of A, I'm going to write 30 equals 1/2. Our base is 8, and then we have some unknown height. So h becomes the variable that we want to solve for. So let's just solve for h. I'll first start by multiplying the 8 and the 1/2. Multiplying by 1/2 is the same thing as dividing by 2. We could also see this as an 8 over 1, and we're multiplying two fractions here. So 1 times 8, when you multiply two fractions, multiply the tops and the bottoms together. So we could say 30 equals 8 over 2. So 1 times 8 and then 2 times 1. Still times h. And then 8 over 2, that's dividing it by 2. So multiplying by 1/2 is the same thing as dividing by 2. So 8 divided by 2 is 4. So 30 equals 4 times h. And then let's just divide both sides by 4. So this will cancel. Now 30 divided by 4, it doesn't divide cleanly. You would get some decimal, but let's find an exact answer. Since they're even, we can at least both divide them by 2. So divided, it wouldn't really work out that way. Let me see. Let's divide each one by 2. So 30 divided by 2 is 15, and 4 divided by 2 is 2. And we're still left now with h on the side. And that's about as reduced as we'll get. 2 is prime. It can only be divided by 1 in itself, and 2 does not go into 15, so we'll leave it there. As a decimal, that would be 7.5. So this is just plugging in. They might give you a few different kinds of formulas to work with. Just write down what you have and plug in, and then solve for what's left. This next section is on solving a few more problems using formulas from geometry. Let's look at the first example. It says a soccer field in the shape of a rectangle has an area of 9,000 yards squared. So that's the area. Its length is 120 yards. And it's asking us, what is the width of the field? So for any of these kind of questions, I would highly recommend just drawing out a little sketch. It doesn't have to be perfectly proportionate as long as it makes sense to you. We have some rectangle. And let's say this is our length and this is our width. And we could have called this the length and this the width. As long as we're consistent, we'll still get the same answer. And so we do have to know the area of a rectangle, which is length times width. So let's start there. I'll write it up here again. Our area is length times width. And what are we given? Well, they said the area is 9,000 square yards, and the length is 120 yards. So let's plug in what we have and see what's left over. So instead of A, I'll say 9,000 equals length times width. The length is 120, and then we're trying to find out what the width is. So that's our unknown. So let's solve for W. It's being multiplied over here, so I'll divide by 120, divide by 120. We'll cancel on the right side. And then 900 divided by 120 should give you 75. So that is the width of the field. So now we know that the length is 120, the width is 75 yards. Let's look at a slightly more complex example. Let's scroll down. So this one says Stewart wants to put a rectangular safety fence around his backyard pool. So it looks like we'll be dealing with another rectangle. So I'll go ahead and draw it out. And we can imagine the pool is in here. He calculates that he will need 120 feet of fencing, and that the length will be 4 feet longer than the width. And it wants us to find the dimensions of this fence. So this time, we're no longer thinking about area, but this is a question about the perimeter, the total amount of fence as we go around. So we can label this again. I'll call this the length. This would also be the length up here. And then this would be a width, and this would be the same width. So if we want the perimeter, we would just need to add up all of these side lengths. So we have 2 of these lengths and 2 of the widths, and then we would add them all together. So that's where the area, the formula for perimeter is coming from. 2 of the lengths plus 2 of the widths. And he says he'll need 120 feet of fencing, so that is our perimeter. The total amount of fencing. So 120 feet. And it says the length is 4 feet longer than the width. Well, let's turn that into a little equation. It says the length is 4 feet longer than the width. So we can describe the length as the width plus 4 feet longer than the width. So now, excuse me, now we can start to plug in the 120 for the perimeter, and then for the length, I'm going to plug in this statement, and we'll see why that's useful. So our perimeter is 120 feet equals 2 times the length, and instead of this L here, I'm going to replace it with W plus 4, since we're saying the length is 4 feet longer than the width. And then we still have this plus 2W. So notice now we've translated the original formula into something that only has one variable, and that's useful for us because then we can solve for that one variable. If we still had the L in there, we wouldn't be able to fully solve for W because we would still have some unknown. So that's the trick. We're expressing everything in terms of a single variable here. So let's go ahead and solve for W. So I'll distribute this 2 to both terms in here. So I have 120 equals 2 times W, and then 4 times 2 is 8. And we have another 2W here. Okay, let's combine like terms. We have two 2Ws, so 2 plus 2 is 4, so that will give me 4W plus 8. And we're solving for W, so I'll subtract 8 from both sides. 120 minus 8 is 112. And then we still have 4W. So let's divide by 4. So 112 divided by 4 should give you 28. And that will be equal to W. Excuse me. So that's our width. So let's actually hold off. Let's answer the full question here. It's asking for the 2 dimensions. So we know that the width is 28, and then we said the length is 4 feet longer than the width. So our length should be 28 plus 4, or 32. So our length is 32 feet, and our width is 28 feet. So we had to take this and go back and plug into how we described length in terms of width earlier. That would be our last step. Okay, let's look at a few involving angle measures of triangles. And these have some special properties. So in example 4, it's asking us to find the missing angle measures. And they show us these 3 angle measures. And one thing we need to know is that the angles within a triangle always add up to 180 degrees. And I'll write that here. So we can take advantage of that fact. Since we have these 3 angles, their sum must be 180. So let's write a little equation. Our first angle is x plus our second angle, 4x plus 9, plus our third angle, which is 41. This all should add up to 180. So let's just solve for x. We have x plus 4x here, and then 9 plus 41. So that'll give us 5x. 9 plus 41 is 50. This is equal to 180. Then I'll subtract 50 from both sides. So 5x. 180 minus 50 is 130. So 5x equals 130. And then I'll divide by 5 on both sides. So it'll cancel here. 130 divided by 5 is 26. So now we need to plug this in to x in our two angles here. Well, this one is just x itself. So this angle is 26 degrees. And then this angle, 4x plus 9, let's just plug in 26 for x. So 4x plus 9, we would say 4 times 26 plus 9. 4 times 26 is 104. So 104 plus 9. So that will be 113 degrees. So in this type of problem, just take advantage of this fact that all angles within a triangle should all add up to 180 degrees. Let's see another example. In this case, we have two lines that intersect, and then we have some angles that are across from each other. And so if you recall from geometry, these two angles that are across an intersection are always going to be equal. We could say that these two angles will also be equal. I think they call them vertical angles. So I'll just say angles across from each other. In an intersection like this, an intersection of two lines, these angles are equal to each other. So we can just set them equal and create a little equation. We have the angle on the left, 6x minus 9, should be equal to the angle on the right, 5x plus 1. So let's solve for x. I'll move this 5x over. So it's positive on the right side, so I'll subtract it from both sides. 6x minus 5x, that'll just give 1 left over. So x minus 9 equals 1. Now let's add the 9 to both sides. So that will give me x equals 10, 9 plus 1. So let's go and plug this in and solve. So this is 6x minus 9. So I'd plug in 10, so that would be 6 times 10 minus 9, which is 60 minus 9. So this will be 61 degrees. I'm sorry, not 61, 51. And we said these should be equal, so let's see. Let's plug in and see if we get the same value. Here we have 5 times x plus 1. And we're saying x is 10. So 5 times 10 plus 1. 5 times 10 is 50. So 50 plus 1 equals 51, which is what we got on the left side, so that's good. So for this kind of question, take advantage of this fact that angles across from each other on an intersection are equal to each other. So just set them equal and then solve for the variable. In example 6 brings in this idea of supplemental and complemental angles. It says the supplement of an angle is 34 degrees more than twice the complement of the angle. Let's first define what these two are, supplement and complement. So imagine we have a straight line and then some line coming off of it like this. That produces two angles, A and B. These are what's called supplemental angles. They all add up to 180 degrees. That's their sum. So that's their property. You can say supplemental angles add up to 180 degrees. You can say A plus B equals 180. So that will be useful. And then complemental angles have a similar property, but let's imagine now we have a right angle. So this is 90 degrees, and then something splits in between. And let's call this angle C and this angle D. So complements add up to 90 degrees. Let's say complemental angles add up to 90 degrees. Or C plus D equals 90. So let's try to work through this word problem. It's a little bit tricky. It says the supplement of an angle is 34 degrees. So let's just call this angle, whatever it is, x. We have an angle. That will be x, our unknown. So the supplement of an angle, the supplement of this angle would be 180 minus that angle. We can subtract it from 180 and we'll get the supplement. And then the complement of the angle we can do a similar thing and say 90 minus that angle. And we're saying that the supplement is 34 degrees more than twice the complement. So let's turn that into an equation. Maybe I'll write it out. So the supplement is 34 degrees more than twice the complement. We said the supplement of an angle is 180 minus x. So I'll say 180 minus x is, so that's like our equal sign, 34 degrees more than twice the complement. So let's start with twice the complement. So twice meaning 2 times, and we said the complement is 90 minus that angle. So 2 times 90 minus the angle. And then it's 34 degrees more, so I should add 34 to this. So the supplement of an angle is 34 degrees more than twice the complement. So that can be the tricky part, just transcribing into an equation. Now let's just solve for x. So I'll distribute the 2, get rid of the parentheses first. So I'll get 180 minus x. 90 times 2 is 180. 2 times minus x will be minus 2x. And we still have the plus 34. All right, let's subtract the 180 from both sides. So those will basically disappear. So it'll be 0 on the left side, so we're left with minus x. That will cancel out, and we'll be left with minus 2x plus 34. All right, let's move this 2x over to the other side. I'll add it to both sides, plus 2x plus 2x. Minus x plus 2x, you can think of that as 2x minus x. So we'll have 1 left, and this equals 34. So this will be the angle that we want, because we said an angle is x. So this time we don't have to plug it in. So if it's a question involving supplements or complements of angles, just keep in mind that supplemental angles add up to 180. So what we did earlier was basically solve this for one angle. Let's say that the supplement of an angle is 180 minus that angle. And then you can do a similar thing for complements. Complements add up to 90 degrees. All right, in the last section, now we're solving a formula for a specific variable. So this is without plugging things in. Still keeping the other variables there, but we're just rearranging them, moving them to the other side. So let's look at this one. First, it has us solve a normal equation. 3x plus 4 equals 19. And it wants us to solve it for x, so let's just do what we've been doing. We have this plus 4, subtract it from both sides. So we'll be left with 3x. 19 minus 4 is 15. Then let's divide by 3. So it'll cancel on the left, and x is equal to 15 divided by 3 is 5. So they brought this back just as an example of how we've been solving equations that have numbers, and we're solving for one particular variable. In this case, it's the only variable there. just the x. Well, we can apply the same process even if we don't have any numbers, if it's all just letters. We have ax plus b equals c. Notice it's in the same form, something times x plus something else. But instead of numbers, we have these letters. But we still have this ultimate goal of solving for x, meaning we want to move everything else over to the other side until we just have x on its own equal to everything else. So we'll follow the same process. I have this plus b, so I just want to subtract b from both sides. Now here, since we don't know specifically what c or b is, we can just say this will be a times x equals whatever c minus b is. We'll just leave it there. So on the left side here, we were able to actually do the subtraction, but when it's still general like this with the other variables, we'll just leave it, we'll say this is equal to whatever that subtraction would be equal to. And then let's continue. We have a times x here, a times x. So to move this a to the other side, we will just need to divide. I'll divide by a. So it'll cancel on the left. And I'm going to divide this whole side by a. So x equals c minus b over a. There's another way we could state this answer. If you have an addition or subtraction over a single denominator, you can split it up into two different fractions. Like instead of saying c minus b over a, we could say that x equals separately c over a minus b over a. You can split it up like that. So these are two equivalent answers. And you may like one form more than the other. But yeah, with the second one, we can imagine we're subtracting two fractions. They already have a common denominator, so we can write it as the subtraction in the numerator over the common denominator. Let's see another example. So example 8. They gave us this new formula. It says u equals 1/2 L times I squared. They say it's a formula that's used in physics, so you may see this come back up one day. And it's asking us to solve this equation for L, meaning we want to just get this L by itself and everything else over to the other side. So it has this 1/2 in front. You could imagine this Li squared is over 1. So let's write this as a single fraction. That might be helpful. So we have u equals, this Li squared can go in the numerator. And we can see this all as being divided by 2. So if we want to move this 1/2 over to the other side, you can see this is a division by 2. So let's multiply it over to the opposite operation. So this would be 2u equals L times I squared. We are multiplying both sides. Technically, we could say times 2 over 1 times 2 over 1, and then these 2's cancel. All right, next, we're still trying to solve for this L, and we have I squared being multiplied. So let's just divide. Divide both sides by I squared, whatever that is, whatever that represents. So it'll cancel on the right side. So let's just write it. I'll stick the L on the left side because we're kind of used to seeing that. So I'll say L equals this statement here, 2u over I squared. So they'll give you some equation, might look a little messy, and then they're giving you some variable that they want you to solve for. So the ultimate goal is just to move everything over to the other side. All right, let's look at one more. This is example 9. Here they give us the area formula for a trapezoid. So we have A equals 1/2 times the height times, in parentheses, B1 plus B2. These are two different bases. And it wants us to solve for B1. That's ultimately what it's asking us to do. So, meaning we want to isolate this variable and get everything else moved over to the other side. So how can we do this? Oops. Scroll back down. Well, this B1, it's inside of this set of parentheses. So we ultimately want to get rid of those. We could distribute this through to both terms. However, since it's already being multiplied on the outside, we can just think about moving these pieces over to the left. So let's first start with the 1/2. Remember in that previous example, we had a 1/2, and to move this, we can see that as like a division by 2. So in order to move it over, we would multiply. So multiply by 2. And then let's keep in mind we want to solve for this. So when the 2 multiplies over, we'll just end up with 2 times A. We still have the H times B1 plus B2. So these are just little labels. It's not like this isn't like 2B, it's just like giving it a name. That's why they put it as a little subscript, this small number next to the letter. So now this is being multiplied by H on the right side. So let's cancel it by dividing both sides by H. So these will cancel. And then on the left side, we have 2 times A over H. And then on the right, we can drop the parentheses. We'll just have B1 plus B2. So now, keep in mind, we're solving for B1. So we just need to subtract this B2 over to the other side. So let's write it like this. We'll have B1 left over. This will be equal to our 2A over H minus B2, because we subtracted it. And now it's solved for B1. So still looks a little bit messy. And there could look a little bit different if we had first multiplied this through to both terms, but you should still get an equivalent answer. So just think about what they're asking you to solve for and get everything else moved over to the other side of the equation. All right, so this was section 2.5. We were looking at some geometric applications and solving questions involving formulas. So we substituted values into a formula to find some unknown. We solved problems using some geometric formulas, specifically around triangles and area. We also solved some problems involving angle measures. So there are a few properties there, the complementary, supplementary angles, and then angles across from each other and an intersection. And then we took some formula given to us and solved for a specific variable. So it's really just like rearranging things, like rearranging pieces of a puzzle. All right, that's it for this video, and I'll see you next time.